Modern society runs on batteries. And as we shift towards renewable energy, they're even more essential. But what are batteries really? It turns out they're just little chemical hills with high potential energy here and low potential energy here. The electrons slide down the hill, doing work as they go. Let's get a closer look at the real chem going on here. I'm gonna dip this piece of zinc metal into the solution. Watch close. Let's make some observations. First, the solution is less blue. Second, the zinc has a black tarnish. Well, we know the blue color comes from the copper ions. So if it's fading, the copper ions are going somewhere. It turns out that's the black tarnish on the zinc. What we're seeing is a reaction where copper-2 ions in solution are gaining electrons to become solid copper. They're being reduced. Meanwhile, the zinc is losing electrons and dissolving into the solution as zinc ions. They're being oxidized. Electrons are being transferred directly at the surface of the zinc metal. Now that's not very helpful because we can't have them do work there. Can we separate this electron transfer and force them through something? Say, a wire, so we can make them do work? Let's take a look at our new setup. This is most of a galvanic cell. On this side, I have a piece of copper metal in a copper-2 solution. Over here, a piece of zinc metal in a solution of zinc ions. The zinc metal releases electrons, which travel through the wire to the copper cell. The copper-2 ions grab those electrons, turning into copper at the surface of the electrode. Now, you might ask yourself, how big is that chemical hill? Well, let's measure it in volts. This is a multimeter. It's like a pinch in the electron hose. It measures how many electrons build up on this side versus this one. 1.10 volts. A commercial AA battery operates at 1.2 to 1.5 volts. But there's a problem. Quickly, the charge builds up. My voltage is getting pretty unstable. The zinc side gets too positive, and the copper side gets too negative, and that stops the electrons from flowing. This is a high-precision salt bridge. It may look like a napkin, but it serves a much more important purpose. I've dipped my paper towel in sodium chloride, and that allows ions to flow between the two cells and balance out the accumulating charge. With this little thing in place, electrons can keep moving, and the voltage remains steady. Now, is the voltage in our galvanic cell affected by concentration? Let's find out. Here are 4 separate solutions of copper, ranging from 1 molar to 0.001 molar. Let's hook each of them up to the zinc and record the voltage. As we dilute the solutions by a factor of 10, the voltage decreases. But if we take the log of the concentration and replot, boom! We get a straight line. This is the Nernst equation in action, which relates experimental voltage to the standard reduction potential and concentration. Galvanic cells convert chemical energy into electrical energy through redox reactions. Separating the half reactions lets electrons flow and do work, like lighting up a multimeter. The salt bridge is crucial in maintaining charge balance. And finally, concentration matters. The Nernst equation shows us how. Batteries, whether in your car, phone, or in a renewable energy system, are just galvanic cells scaled up. Chemistry powers our modern world, and it all starts with a little electron transfer. That's real chem.